You ready? Okay, thank you, everyone. Sorry for the delay. We're having some technical difficulties. I would like to welcome you all to our Athena seminar series. And today we will have Dr. Neiwen Ling present. She's currently a postdoc in the Efficient Computing Lab at Yale, working under the guidance of Athena PI Professor Lin Zong. She completed her PhD at the Chinese University of Hong Kong, and her research falls in the intersection of edge computing, machine learning, cyber physical systems, Internet of Things, and real-time systems, with a focus on developing time-sensitive AI systems for embodied agents. She has published many papers at conferences and won many awards. I won't list everything. So with that, I'd like to welcome Neiwen. Please go ahead.
Thank you. Thanks for the kind introduction. I'm excited here to talk about my research on making AI systems more time sensitive. Today, AI models like a deep learning foundation model, large language model, increasingly powers physical devices and widely deployed in our daily life. For example, Tesla utilizes deep learning for perception in their cars. And Apple launches a new version of iPhone with Apple Intelligence. And most of robotic companies like OpenAI Figure and Unitree utilize the large language model to power their robotic products to achieve better human-computer interaction and complete more complex tasks. So what is a physical AI system? The physical AI system consists of two parts, the AI models and the physical agents. And the AI model is a very important part that powers the physical agents like autonomous vehicles and robotics. Specifically, there are another two parts of physical AI system about sensing and action. The sensing module utilizes sensors, for example, camera as eye, microphone as ear, to interact with, to sense the physical world. And this part is powered by model for perception. For example, BLEEP for image understanding, EURO for detection, UNet for segmentation. And another part is action. This part utilizes the grips, servo motors, to operate physical objects. And this part is also powered by models for control. In the past, most of research work utilizes reinforcement learning like DQN, PPO to generate the next state of robotic action. And now with the emerging large language model utilization, some more and more academic and industry work utilize the large language model like GPT-4, Llama 3, Phi-3 to generate the robotic plans. But deploy the physical AI system in our real world, we need to address multiple system challenges. One important challenge is time sensitivity. Time sensitivity refers to timely processing for all AI tasks in the system. This is pretty important for physical AI system because the tasks for physical agents are time critical. For example, the autonomous vehicles need to detect the obstacle before the potential collision. And also, the robot dog need to respond within certain time duration. Otherwise, it will make the user angry. To achieve a time-sensitive AI system, we also need to address other system challenges like efficiency, scalability, and adaptivity. For example, we need to achieve high efficiency to minimize the model inference latency. And also, we need to handle dynamic scenarios with new incoming tasks. We also need to design a framework with high scalability to support growing task demands. In my past and current work, I mainly aim to solve those system challenges, and they can be classified into two parts, the sensing parts and the action parts. And I solve multiple specific research problems in both two parts. For example, in sensing part, I study how to achieve high CPU-GPU resource utilization on edge platform, and also solve the resource contention among multiple perception tasks. I also study the data synchronization among multimodal data. And for the action part, I study the efficient programming language to generate concise robotic actions, and also explore its efficient generation execution mode with and the time-sensitive serving mechanism to provide timely service to robotics. And in today's talk, I will mainly focus on those two parts, the CPU-GPU resource utilization and the serving mechanism. This is the outline for today's work. I will introduce the time-sensitive large language model serving first, followed by the closed processor deep learning inference. Let's start the first part about the large language model serving. The motivation of this work is the emerging large language model powered robotics. This is a demo video developed by Guojun in our lab. In the left side, this is the external view in the testing environment. And on the right side, this is the drone view from the cameras on the drone. This part is the human input for the command. And we can see when we send a command like try to find edible objects, the command together with the images will send to the large language model on the server, and then large language model will generate the action plans. We can see it again. With the generated robotic actions, the drone will turn around and target at the apple, then move forward to the target object. And we can see not only academic research, the industry like OpenAI also collaborate with Figure to develop a large language model powered humanoid robots. And they plan to replace the human labor in one BMW group plant. So how many Figure robots will we need for one plant? Currently, one plant assembles more than 1,500 vehicles each day. So the answer would be at least 100 level. Given this background, we envision in the future a large number of robotic agents will continuously and concurrently send requests to an large language model service. Given multiple requests, here is open questions. How could we provide timely large language model service to satisfy different time-sensitive requirements for robotic agents? The large language model service can be deployed at an edge server in the plant or on a cloud server like Amazon. Let's first introduce the time-sensitive requirements of robotics. We survey some human-computer interaction literature and also robotic literature to figure out the time-sensitive requirements for different robotics. For example, for a robot to finish the task, picks apple for us, if the response time is smaller than 1 second, we regard it as an excellent behavior. But if it's larger than 1 second, it may be tolerable. But when it appears to the infinite large, it may be just garbaged by the user. And for a drone to avoid the animal, if it can respond within 200 million seconds, it will be a safe situation. But if it's become larger and longer and longer, the dangerous level will also increase. In our work, we utilize a time utility function to quantify the specific time-sensitive requirements of robotics. You can see this is one TUF for error handling. It will have an initial time utility value, beta, and if the response time of robots passes the expected response time, it will decrease with a factor alpha. And we can use this unified format to represent different timing requirements with different parameters of beta, alpha, and expected response time. Now, let's look at how current large language model serving system supports the multiple robotic requests. Currently, the most naive approach is sequential processing. It means it will generate a response for each request one by one. And some naive batching is batch several requests for processing at one time, and then the later request will only start generation after the completion of the last batch. For the most sought-out approach, like VLLM and TensorRT LLM, it utilizes the continuous batching. It means a new task can be directly processed once there are available resources. But also the serving systems falls short in handling time-sensitive requirements, and also they have an assumption that they will generate the entire plan without interruption. Later, we will show what's the shortage of those systems. We found there is an opportunity to optimize the large language model serving system to support timely processing of requests. Since the redundancy between the robot plan generation and the execution phase. As we can see, when we generate one robot plan, when we generate the first action move up, it will take 1.5 seconds to finish execution. So there is a huge redundancy between the robot plan generation and the robot plan execution. For the second action, like a move forward, it only needed to be generated before the start of action E2. So utilize this opportunity. Our main idea is segmented large language model serving. Here I give an example about the segmented LLM serving. There are two robot arms. And when we generate the first action for the robot arm 1, we can stop here and generate the plan for the second robot, like pick a pencil. And when we finish generation of the second plan, we can go back to the first robot arm and generate the following plans. In this way, the second action in robot arm 1 is successfully generated before the completion of the first execution. But at the same time, we generate the plan for robot arm 2 more earlier. So that it can be start execution earlier. To deploy our main idea, we design a segmented large language model serving system called Timely LLM. With multiple robotic agents, it will send the continuous request with timing requirements. It is TUF in our work. TUF means the timing requirements of robotics. And then the server will prioritize each request and put it in the priority queue. We will talk about the priority assignment in the later slides. And given the priority queue, we will use the latency-guided continuous batching to determine whether to process one request or not. For the processed request, we will segment generate the response, and it's based on the generated content. For example, we will generate one available actions for execution, and then when we generate the segment for one action, it will be directly sent to the robotic agent for execution. And at the same time, if it's not the last action, the suspended generation will be reassigned the priority and put back to the priority queue. Now I will introduce each component of our system. First, about the segmented generation. For a normal large language model generation, we will generate all tokens for the response and then detokenize it into the natural language. And for our segmented generation, we will generate one token and then detokenize. We will use a stop checker to verify if the generated response is available action. If it is, we will output the generated segment. If it's not an available action, we will just generate the next token. In this pipeline, we need to the input and the generated response to generate the next token. It will be very time consuming because we need to conduct the pre-filling for the suspended generation. To solve this problem, we utilize the KV cache storage together with token ID storage to minimize the overhead of segmented generation. With segmented generation, we have the output in segments. So then I will talk about how could we schedule those segments. For a standard without our approach, the standard approach is maximize the time utility of response time for all received requests. That will require us to estimate the generation time for the whole request. It is very challenging for large language model inference because the output size, output token length is not fixed by a large language model. And in our approach, we only need to maximize the time utility of waiting time across all segments. This is the waiting time of the first segment. and this is the waiting time for other segments. And this maximize the problem is a classical utility accuracy optimization problem. It is NP-hard, which is proven in multiple literatures. And existing work designs the priority assignment based on potential utility density to solve this problem. Similarly, we build our solution based on potential utility density while addresses the unique challenges in our segmented generation. This is the equation for the priority assignment. This part is the time utility of the one segment, and divided by the generation time is the utility density. We also add a slack time to different tasks with the same initial utility but different expected response time. Call back our main idea in this work. We want to generate the next segment before completing the current plan execution. And we utilize the time model to predict the robot execution time, and then feed it to the estimated waiting time and the slack time in the priority assignment, so that a segment with longer robot execution time intends to have a lower priority for the execution. With the priority assignment, we next determine the batch size for the model inference. It's challenging to estimate the influence of batch size for model inference latency. And what we adopt here is to try to figure out whether to add new requests for processing based on two conditions. First is about the GPU memory availability, and second is the estimated latency impact based on the worst case execution time. It means we will estimate the worst case execution time of the most urgent task and compare it to its expected response time to determine whether to add a request for processing or not. To evaluate our system, we have collected a data set, collecting the data from the real robots. Currently, there is no existing data set can evaluate the multi-agent large language model serving system. So we collect the trace including the plan generation time and also the plan execution time from the real robot. As we can see in this table, we collect a trace for different tasks, like look for the cat or check for keys or wallet. And with those traces, we can combine them differently to format a workload in this way. And with different combinations, we have different workloads for evaluation, such as mixed TOF and different levels of parallel degree. We implement our system based on the current SOTA serving framework, VLLM, and test it on a NVIDIA GPU. And we also compare our work with the VLLM and other alternative variant of our method. For example, utilize the first come first serve and EDF approach. And this is the evaluation results of our system. We can see from this figure, this is the time utility achieved by our system and baseline. And this is the waiting time. Waiting time here means the total delay introduced by the large language model planning. We can find our approach achieve better time utility compared with VLLM because we have segmented the generation and send the plan to the robot for execution immediately. And even for the VLM stream, our approach is better. The VLM stream transmits the response in stream. It means the robots can execute the plan immediately when it's generated. But our approach optimizes the service system from resource contention. It means giving multiple LLM requests, we utilize the redundancy between the plan generation and the execution to resolve the resource contention. In this way, we have better performance in time utility compared with VLLM stream. And this is the statistical data. We increase the utility by 1.97 and reduce the waiting time by over 80%. Now I will go to the next part about closed processor deep learning inference. The motivation of this part is emerging heterogeneous processors on edge platforms. For example, the NVIDIA Xavier utilizes 8-core CPU and 1 GPU, and the Raspberry Pi utilizes 4-core CPU and 1 GPU. But currently, we always deploy all the deep learning tasks on the GPU, which makes the CPU idle sometimes. The problem we aim to solve in this work is how to utilize both edge CPU and GPU for timely DNN inference. This is pretty challenging because the CPU is if we directly deploy the deep learning on the CPU is not efficient for inference. The main idea of this work is the construction of dual block. Dual block is a new model inference abstraction. For example, block here means one or multiple deep learning layers, and one dual block means two versions of this block, one for CPU version and another for GPU version. It means whenever which processor is idle, we could execute the corresponding version on the process, so we can achieve efficient utilization of CPU GPU resource for most urgent tasks. Specifically, given a DNN model, we will participate into multiple blocks, considering the communication time among different layers and also the operator fusion rule. And for each block, we will construct a dual block for execution. At the runtime, we also design as a dynamic closed processor scheduling. It means it will decide the execution order of the DNN model and the block once according to the idle state of different processors. For example, if we execute the dual block on CPU, it will execute the CPU version. And I will skip the detailed design and come to the evaluation part. So we evaluate this system on 3 edge platforms and 1 robot car. And for this part, we utilize the image sampling rate as the deadline setting. It means we try to finish one image processing before the coming of the next frame. And this is the evaluation results in the robot car. We can see with different background workload, the static means the robot car is static, and and this one means the robot car is moving. And we can see, given the different workload background workload, we can still achieve less than 5% data missing rate. This is because we efficiently reduce both CPU and GPU execution time and waiting time. Okay, let me sum up today's talk. Today, I start by time-sensitive large language model serving and then followed by the close processor deep learning inference. So what's the next step for us to explore time-sensitive AI systems? I'm excited about two directions. The first one is the time-sensitive AI agent memory management. Besides the sensing and the action part, the memory is very important when we deploy the physical agents in a continuing physical environments. The memory includes the short-term memory like KV cache and also the long-term memory like rack. The open question here is how could we efficiently cache the variable information for providing timely service? So our basic idea is leverage urgent guided predictor to predict and cache the most potential required information. This is based on my design philosophy in my past work. We need to decide the ordering and the priority of the tasks based on the task timing requirements. In the past work, I worked on the computing, so we decided the processing order. And similarly, in the memory management, we could still decide the cache order based on the time urgency and then design a predictor to figure out the most urgent potential cache information for the most urgent task and put it near the computing for quick information retrieval. And the second part is understanding the time urgency from physical dynamics. Besides the computing and memory, it's also very important to have the time sense of the task urgency. It's very important to design a robust understanding of time urgency, so that the physical agent itself can figure out what's the most urgent task and whether we should prioritize this task or not. And the understanding here consists of sensing and mapping. So sensing means how could we tell whether this task is urgent or not? For moving objects is we can just use the object speed to evaluate the urgency of the task. But for the human reaction and behavior, we need to recognize the human emotion to figure out whether this is urgent or not. But this is all have some existing work about the human emotion recognition or developing physical mode for estimate the object speed. But the most challenging part is mapping. How could we map the user requirements to precise task timing requirements? My main idea here is utilize some historical personal preference together with the runtime detection results from the sensing, and then to map the dynamic urgent requirements into the precise data. Besides the physical agents, the time-sensitive AI system is also very important in a lot of real-world domains, like AI for stock trading, or it means we need to make time-sensitive decisions to figure out the best opportunity to trade. And also for AI video creation, we need to optimize the live video within certain time duration. Otherwise, it may cause the service interruption. Also, for spacecraft control, we also need to guarantee we can adjust the trajectory within a certain seconds. And that's all for today's talk. Thanks for listening. Is there any questions? Oh, I
Can ask people if online have questions.
okay.
So she is asking us different questions. Anybody in the room have any questions?
I have a few questions.
Speak louder.
Okay, like, for your first work, you use a cost function to evaluate the quality, right? We'll go back to that functions.
Okay.
Like, I wonder why the quality is low like this.
Oh, wait a minute. You mean this one?
Like, I would evaluate the efficiency of this function when use some trace or benchmark to evaluate this question.
Oh, could you say it again?
Like, why the high utility functions look like this?
Oh, you mean why we use this format to quantify the time utility function? Actually, the time utility function is a non-increasing function, and this one is the most unified format. Because the most important here is to quantify the initial time utility and also the expected response time. We can use different curve to represent the time the utility decrease, or as but this one is the most unified one. We can correctly catch all the important informations in our time utility.
So is the standard functions like how still create such a function? Like, I'm not really sure. Like for example, you use a linear functions when you increase, like when the response times exist the requirement, right? So it will is okay. For another part, like for the second part, is a linear function. Is that a standard functions? Like, is that like? I'm not pretty sure whether it makes sense. That's me.
I see. Actually, you can also utilize other utility functions, because the design is not limited to this kind of utility function. So our assumption utilized in our design is the characteristic of non-increasing of the time utility function. So other function like with these characteristics can also be fit in our system design.
Also on this slide, the first part, the flat part, is there a particular reason why we give it a kind of tolerance so that before a certain expected time we don't penalize it? Is there any like rationale behind it?
Yeah, exactly. This means we do not, even we have a quicker generation time, the utility we gain is still the same. Second work.
Yes,
Okay.
so. When you like explain about the substructure, you have good use. So you said you have like CPU and CPU tasks. So could you give some examples about these tasks that we like divide into different CPU? And
Oh.
second of all, what would happen, let's say we have a task that is CPU heavy, for example, like mass modification, and when the load will be like 100%, but we don't have something to do on the CPU side. Would you like offload tasks from the CPU to CPU in that case?
Yeah, that's actually is what I explore in this work. We utilize the deep learning tasks for object classification like VGG, AlexNet, ResNet, to verify our system performance. And the deadline for each task is determined by the image sampling rate. It means we will finish processing one task before the coming of the next frame. Thank you.
Just a clarification question. The dual code. Do we just have multiple copies with like the same neural network part on both GPU and CPU? And you basically just direct it to whichever resource based on whether there's a bottleneck?
Yeah, we utilize the technical like NAS, neural architecture search, to determine the optimize the model architecture in different processors. And at runtime, we will determine which block version to execute based on the current status of different processors.
But does GPU necessarily contain the same copies as CPU? Network, or it could be just CPU?
Oh, they are different.
Okay.
Yeah, they are optimized for different processors.
Oh.
Any questions from the audience on Zoom?
One more questions. Yeah.
Yeah, sure.
Search for processor specific, like neural network modeling. Would that, what is the loss function look like in that situation? Because here you're talking about performance, not like the models, like the actual decrease in accuracy or increase in accuracy. You're talking about like the capacity of the like CPU or GPU that has.
Yeah, when we use the NAS to optimize the deep learning architecture, we still use the same loss function of the original one. And since is this answer your question?
Sort of. So basically, you're not really like loss modification in any sense inside the CPU.
Yeah. I no joint. You mean the joint optimization, right? Yeah, no, not in this way.
Okay, like if like any audience on the Zoom, if you have any questions, please just voice out. If no further questions, I'll just like ask one question. Can you go back to the Timely LLM, the server page? Like, there's like two lines of arrows. Like one is the original like generate all tokens, and the other one is generate one token and add a additional checker.
This one or this one?
The page 23.
Okay, this
Oh
one.
yeah, thank you. I'm just like curious because like the stop checker here adds additional computation. So like why the lower one is kind of more time efficient compared to the upper one?
Oh, the main benefit caused by the segmented generation is the interrupt of the generation, so that it can solve the most urgent tasks.
Oh, I see. So
Yeah,
so
but
the overall like time, the lower one will be longer compared to the upper one, but it's just more timely.
Yeah, because it will have some overhead for the segmented generation. But we also evaluate the overhead in our paper. It's tolerable compared to the entire generation time.
Okay, thank you. That makes sense. Okay, let's thank Neiwen for her wonderful presentation. Yeah. Okay, and I think that would be it. Thank you very much.
Thank you.
Thank you. Hey, please, think about